My topic is protected probabilistic classification, and it is just about binary classification, the simplest case. And at the end, I will talk about possible extensions. So here, our goal. So what we notice in our collaborations with all kinds of companies is that as soon as you train your predictor, the distribution of data changes, and then you need to do something about it. In my previous talk, I mentioned change detection, but here our goal is different. Instead of trying to detect a change, we are trying to improve our predictor. And it turns out that you can use testing to improve your predictions. So in my previous talk, I was talking about using prediction to do testing, but here we can make the full circle. We can use testing to improve our prediction. Okay, but this work is inspired by conformal prediction, but it is not about conformal prediction. It's about improving just regular prediction systems. So suppose we have some prediction algorithm, and we train it on a training set, and we get some predictive system. So as I said, we are interested in the case of binary classification. So our labels are binary, wise binary labels 0 or 1. And our predictions are P1, P2, and so on. They are numbers between 0 and 1. And it's the predicted probability that the true label is 1. Okay, so suppose we have some base predictive system, the system we trained. We call it base. But then suppose we run some conformal test martingale, like it's a simple jumper, our standard martingale, which has been used in many papers. And we are successful in gambling against those predictions. So in the case of simple null hypothesis, and here our null hypothesis is simple, it's just this predictive system F we are gambling against. A martingale is a likelihood ratio. So it's F prime divided by F for our null hypothesis F and some alternative F prime. So the idea is just to use this F prime for prediction. And it will be better than F, at least in the sense of log loss function. If S is successful, if S is much greater than 1, then F prime will be much better than F in the sense of some popular loss function, log loss function. Okay, so let me tell you how this algorithm works, but to understand the details, please come to the poster. So here we are trying to improve our predictions. So we are trying to turn our prediction P into some F of P, where F is a calibrating function. We are trying to calibrate our prediction to make them better. And so we are interested in this family of calibration function. So they map 0 into 0, they map 1 into 1. But if epsilon is greater than 0, it will look something like this. So we are compensating, we are correcting for P being underestimates. So we increase P. If this is our P, we increase it. So, but here we don't know what epsilon we should choose. This method, it adapts to a good epsilon. So here what we do, we don't know what a good epsilon is. So we let epsilon range over some small set of possible epsilons. So here it's 0. 0, it's no calibration at all. -1, it's a very strong correction for overestimates, and 1 is a very strong correction for underestimates. And we have another parameter which is called jumping rate. Okay, so here this is what the algorithm looks like. So it's actually very intuitive. So you have those calibrating functions f epsilon, and you don't know which one to use. So you maintain some weights for those. So c epsilon are our weights. And you keep updating the weights. So here, it's very similar to what people do in prediction with expert advice, if you heard about this area of machine learning. Okay, so you have this algorithm, and you can build it on top of any martingale. But this is not a martingale. We are not gambling against our predictions. Here, what is shown, I'm not going into details, but what is shown here is f prime. So here we are given these base predictions, P1, P2, and so on, and we are trying to improve them. We get P1 prime, P2 prime, and so on. So as you can see, Pn prime here in this algorithm, it's computed as the weighted average of the improved predictions. But you don't know how to improve your prediction, which f epsilon to use. So you take the predictions recommended by each of the f epsilon, and you average those. And it's a weighted average. The weights are c epsilon. So here you're just normalizing your weights, and here you are updating your weights. Okay, so this is what it looks like. I don't have time to go into the details of this algorithm, but I hope you can feel what it's doing. So it's just some kind of adaptive calibration. So let me just, to conclude my presentation, I will show you some pictures. So pictures are about the bank marketing data set. So it's very popular. And what is good about this data set, all observations are listed in chronological order. We know this. Because in many data sets popular in machine learning, you don't know what the order is. Maybe it's not chronological, but we want to model this standard industrial process when we have some data and when the distribution changes. So here the order is chronological, and we are using it. So we take the first 10,000 observations in chronological order. The overall number of observations is like about 45,000. So we train a random forest on it. Random forest performs very, very well on this data set, just a scikit-learn function. And then we truncate the predicted probabilities. So we are also interested in the log loss. And if the predicted probability is 0, but it's wrong, your loss becomes infinite. To avoid it, we truncate our probabilities. So this is our base system. And now if we gamble using the simple jumper test martingale against those predictions, you can see we become very, very rich. So this is the trajectory of our simple jumper test martingale over the test set of size 35,000. So the final value is on the log 10 scale. So the final value is astronomical. It's like 10 to the 920. But let's see how it shows. So the log loss definitely goes down, but let's see how it shows in the ROC curve. So the ROC curve is a particularly useful measure because this data set is so imbalanced. So what you can see, this is what happens if you use your original predictive system. And here what happens if you protect it using simple jumper, if you use the algorithm I discussed earlier on top of it. And you can see the difference is substantial. Okay, and let me tell you directions of further research. So first, we need to try it on more data sets, which we already started it, but it's consistent. On another data set, we get very similar results. And also, we should try more martingales, like the martingales I discussed in my previous talk. So like sleeper stayer and sleeper drifter, and see which martingales perform well. Okay, thank you very much, and please come to the poster.